Hello, I am Doğuhan. I am doctoral candidate number 8 in GECKO Doctoral Network. In this video, I will try to summarize my PhD topic. So, let's start with the motivation behind my PhD. Transient acoustic simulations are used in many different areas, such as auralization problems where human hearing is simulated, or it can be used to assess the noise emitted from a moving vehicle, or more broadly, it is used to analyze sounds emitted from time-varying sources. In those applications, geometries are generally complex and require much smaller mass size to capture all the details. This is especially important since the reflection from those complex surfaces can change the results drastically. Moreover, these complex geometries can be in motion or may be used in shape optimization problems. Both of these cases require recalculating the mesh, which is very expensive and can take the most time for an analysis. One solution is to use isogeometric analysis or IGA, which is the main aim of our doctoral network. Main idea behind IGA is to use CAD description of geometries as shape functions in element type methods, such that the CAD geometry can be used in the element methods without meshing the geometry. With this motivation in mind, let's look at my objectives. First, I would need to do numerical acoustic simulations. There are two main choices for that, finite element method and boundary element method. Each has their own advantages and disadvantages. Next, I need to conduct time domain simulations. FEM is slightly better for that task since time stepping is less expensive option for the solution. However, to describe unbounded domains, FEM needs special boundary condition treatments, while for BEM it is already included in the formulation. Next, we need to apply model auto reduction to handle the industrial scale examples. For FEM, this results in significantly smaller matrices, however, they generally lose their sparseness property. For BEM matrices, size reduction is smaller, but they allow for reduction in time direction, so combining this reduction with already smaller system size using BEM might be more beneficial. Lastly, IGA. For FEM, direct application of IGA is harder, so it is better to apply it through other techniques such as immersed methods. For BEM, it is more IGA ready, but it has its own problems. For both of these cases, applying IGA on top of already complicated methods require good justification. For that, we can look at the advantages of IGA. Since other doctoral candidates gave general advantages of IGA, I want to focus on specific advantages for my case. First, it allows us to capture similar sized elements while capturing the same amount of detail, as shown in the sketch. This gives us more control about the system size and the accuracy of our solution. This also gives us more control on the stability, since elements with different sizes can cause instability for time domain solution. Moreover, time domain simulation is affected by high frequency solutions, and IGA generally performs better for high frequency solutions than classical finite element method, due to higher continuity between the elements. Since those advantages seems to apply to both FEM and BEM, both methods has their advantages for different problems. So I would like to develop both methods in parallel so that I can use the more advantageous method for the problem at hand. However, my more recent focus is on shifted boundary method for finite element, where I am in collaboration with doctoral candidate 1. Thank you for watching the video. I am excited to share future updates with you.